Hello and good evening, everyone. Welcome to this breakout session as part of the Digitalize in Stockholm 21. My name is Fateme Rahimian and I'm happy to be the chair of this session, which is dedicated to AI in secure and sustainable systems. We will have 3 talks in this session. All of them are pre-recorded. And it is my pleasure to introduce to you Xianwen Xu, Marco Chiesa, and Musart Balio to introduce their projects to you. Each talk will take up to 6 minutes, so we will have roughly 10 minutes at the end of this session to answer your questions. Please feel free to write in the chat and we will take up your questions live after the talks. Let's begin.
Hello everyone, I'm Qianwen Xu, Assistant Professor in Electric Power and Energy System at KTH. It's a great pleasure to present at Digitalize in Stockholm. My project is autonomous coordination and control of smart converters for sustainable power systems. This project is a collaboration between electric power engineering and mathematics at KTH. Our electric power system is changing. To achieve the national target towards the 100% renewables by 2040, there are increasing integration of renewables into electric power systems. Unfortunately, the intermittent renewables increase the risk of grid instability with the voltage fluctuation, frequency deviation, and inertial issues, which will limit the further integration of renewables. On the other hand, the renewable interface converters offer new promising methods to provide various functions for grid support, like the voltage support, frequency support, and inertial support functions. To efficiently and successfully utilize the grid support capabilities of converters requires optimized coordination of a large number of converters. However, it is a significant challenge. First, the converters have different functionalities for grid support. As mentioned, voltage support, frequency support, or inertial support functions. Then, how to decide when to operate at which function for so many converters to optimize the grid performance is challenging. Next, a large-scale power grid have hundreds or thousands of converters. Then, the communication and computation burden for coordination of so many converters is super large. Then, how to develop a communication-efficient solution is an urgent challenge to be addressed. Our belief is that digitalization and AI will play a key role in developing smart control mechanisms for converters for the grid support. Therefore, the objectives are to develop smart and autonomous power converters for optimal support of electric power systems, and to build a new control framework based on digitalization and AI that will enable smooth integration of renewables. To achieve these goals, we will develop a novel combined optimization and control algorithm to achieve optimal grid support functions, and an AI-based scheme for autonomous control of smart converters for communication-efficient coordination. The results will be verified and demonstrated in a real-world smart microgrid hardware platform at KTH. The outcome of this project is expected to provide the scientific foundations of grid support based on smart converters needed to construct tomorrow's smart power generation systems. Add significant value to digitalized electric power industry, including grid data analytics and advanced cooperative control mechanism, and enhance the resilience of electric power systems with large-scale integration of renewables for the sustainable and smart society. Thank you very much for your listening.
Hello everyone, my name is Marco Chiesa and I'm really excited to be here today. This is a very short talk, so let me get directly to the bottom of the problem with the following simple question. Is the internet secure? Is it secure to those cybercriminal entities whose aim is to disrupt critical services? The internet has been a lifeline for all of us during pandemic time. So we really need to guarantee that services operate over the internet without being affected by cybercriminal activities. But let me ask you the following. How hard can it possibly be today for a cybercriminal entity to bring down a trillion-dollar company? So it turns out that it's not that hard, and that any small network in the world can possibly dream about doing it. All of Google traffic has been hijacked by a tiny internet service provider ISP located in Nigeria. And this was not 15 years ago, this happened just in 2018. And you're probably mostly familiar with April 2020. We were all unprepared at the peak of a pandemic crisis. And a far remote network brought down traffic for the equivalent of $6 trillion cloud companies that hosted the vast majorities of services using a so-called routing hijack attack. Few weeks later, the hospital system in the region of Paris also suffered a devastating attack that disrupted its communication services for several hours. Routing attacks have plagued the internet for decades. These attacks have affected financial institutions such as Visa and MasterCard, have affected the critical components of the internet, have been used to steal cryptocurrencies, have been used to perform citizen surveillance, to intercept mobile traffic, and to steal public key certificates. So you're probably all familiar with that lock, the green lock that we have on the browser. If the lock is green and the URL is correct, then our transactions are safe. Unless there is a cybercriminal entity who managed to steal a certificate for that organization, and it's now impersonating that organization. So this problem has been first unveiled in 2015, and even to these days, there's not really a fix to this problem. So how can we secure the internet? Preventing cyber attacks is complex. With billions of packets traversing a network, distinguishing whether each single packet is legitimate or not is challenging. A natural question that we asked in this project is whether machine learning, with its ability to classify large amounts of data, can help us. Applying machine learning to networking data is, however, non-trivial. Network technologies are ill-suited for extracting information from the network. For instance, most of today's devices can only sample a few packets out of a stream of packets, and that's not sufficient to secure the internet. In this project, we leverage next-generation high-speed programmable network devices that for the first time allow us to inspect each single packet traversing a network device and to generate summaries that can be fed as input to external machine learning systems. The second challenge is the inherent volatile nature of network data. Traffic may enter and leave a network in tens of micro or milliseconds. And this really opened the door to a new research direction in which we tried to move machine learning computation as close as possible to the network. In this project called EMERGENCE, we aim to build a framework for applying machine learning at high speed to take on network cybersecurity problems and to study the related conceptual scientific questions. In Emergence, we will employ a network of programmable switches and a pool of general-purpose computational resources that can run the most complex parts of the machine learning machinery. The project is divided in 3 parts. In the first part, we aim at aggregating and extracting relevant traffic information from the network. And we try to move as much of this pre-computation into the network for a simple reason. Power consumption per gigabits per second on general-purpose CPUs is 20 times higher than on high-speed networking devices. In the second task, we aim at identifying which characteristics of the network are relevant for solving a specific security problem, to extract that information and to feed it as input to a general-purpose machine learning classifier where we perform training and inference. We have built the entire pipeline. We have a prototype of this pipeline, and we are currently evaluating its performance, trying to detect anomalies such as routing hijacks and misconfigurations. So to conclude my talk, we have built the first machine learning framework for analyzing high-speed network data for cybersecurity purposes, and we are now evaluating its effectiveness using different types of pilot studies, such as detection of anomalies and misconfigurations. So that concludes my talk, and I thank you very, very much for your attention.
Hi everyone, and welcome to the talk. My name is Musard Valio, and I'm an assistant professor at KTH. Today I'm going to tell you about SOS, our project on empowering user control over sensitive IoT data. This project is together with my colleagues Fatema Rahimian from RISE and Nikolaya Paladi from LTH. Internet of Things, or IoT, is a very popular buzzword these days. It refers to the various services and devices that are connected to the internet. Examples include smart homes, connected cars, surveillance cameras, heart monitors, and more. Such connectivity is really great, but unfortunately users lack control over their digital lives. For example, you could have a heart monitor connected to the network, but this is of limited use unless the heart monitor notifies the user, for example, whenever the heart rate of a patient exceeds a threshold. To address these shortcomings and boost the full potential of IoT platforms have been created. These are cloud-based platforms that execute code, or apps as they are called, to implement useful functionality in the context of IoT. For example, one could implement an app that notifies the doctor automatically whenever the patient's heart rate exceeds a threshold. The figure on the left gives an overview of an IoT platform with various services and devices connected. For example, you could have a device that measures the CO2 level in the apartment, and the IoT app could allow you to implement the communication between your phone and the device, for example, notifying you whenever the CO2 level in the apartment exceeds a threshold. Several such platforms exist, both commercially and open source. Popular examples are IFT, or If This and Then That, Zapier, Amazon AppFlow, Microsoft Power Automate, and Node-RED, which is an open source version. Now, this is all great, but unfortunately this model also weaponizes the attackers. There are 2 main problems with this model. First, the apps that realize the communication between different IoT services and devices may come from third parties or even malicious makers. This leads to what we call person-in-the-app attacks that compromises user security and privacy. In fact, we show in our prior work that major IoT platforms are vulnerable to such attacks, leading to disruption of services, stealing and modification of user locations, photos, voice assistants, and more. The second problem is that these apps rely on a public cloud platform, leading to what we call person-in-the-cloud attack. In fact, now the cloud has full access to the user's sensitive data, which is dangerous because it could lead to oversharing of this data with third parties, or also leaking it to malicious parties in case the cloud is compromised or simply malicious. And in fact, we sort of learned this the hard way here in Sweden, if you remember a few years back, with the infamous data breach that affected the Swedish Transport Agency. Moreover, once the user chooses one of these platforms, they are sort of tied to one single cloud platform, limiting the usability, for example, when it comes to migration of data between clouds. Now, given the state of the affairs, the question is, what can we do about it? This is where our SOS project comes in. To address the challenge of malicious code from third parties, we develop techniques for security vetting and secure execution of IoT apps. We do this by either breaking the malicious flows, for example by executing these apps in isolated environments called sandboxes, or by tracking the flow and stopping the execution whenever something malicious is about to happen. Technically, we develop techniques based on static and dynamic code analysis and fine-grained access control to enable security in these platforms. To address the challenge of public clouds, we'll rely on the area of confidential computing. Specifically, we use the so-called trusted execution environments, which are either hardware or software extensions which allow to execute both code and data protected in public and potentially untrusted cloud environments. Now, a question you may be asking at this point is, why should we care about this? Well, if you're an end user using one of these platforms, then you will benefit from secure and privacy compliant services, hopefully increasing your trust in emerging technologies. If you are a company deploying the technology of SOS, then you will increase your competitive advantage against other companies and, as a result, your revenue, for example, by providing a new technology that is secure by construction. Moreover, we believe that society at large benefits from powerful automation provided by IoT apps, and we have chosen in this project to focus on digital healthcare and digital education as the prime application domains. Once we have such architecture in place, we can focus on a variety of application domains. However, to demonstrate feasibility in this project, we have chosen to focus on the areas of digital health and care monitoring, as well as in the area of digitalized education. In case you see fit of this architecture in your particular application domain, please come and talk to us. In summary, IoT platforms are really great, enabling exciting and useful application in the domain of IoT. Unfortunately, existing platforms are subject to attacks from malicious actors, leading to massive exfiltration and corruption of sensitive user data. In SOS, we develop technology that allows to keep all the advantages that come with IoT platforms, yet it enables to do this in a secure and privacy-compliant manner. Thanks for listening, and we look forward to your questions and comments.